Okay, let's dive into this. Solar power, I mean, it's hit this incredible milestone, right? A terawatt scale globally.
It's huge.
Panels are just popping up everywhere, roofs, massive desert farms. It really feels like a massive success for clean energy.
Oh, absolutely. A true success story.
But, with that success comes this, well, this unavoidable question. What actually happens to all those panels when their time in the sun is finally over?
That is the critical question we need to tackle now. The first wave of solar tech, it was really laser focused and quite rightly on making panels that were super efficient, affordable, and, tough enough to last decades.
Makes sense.
But now, with literally billions of panels heading towards their end of life in the coming years, how we handle the materials inside them becomes just as vital as the power they make.
Right, and that really is the core challenge we're digging into today. We're looking at some really insightful research that tackles the next big thing for solar: design panels to be genuinely recyclable, like building that capability right into the material from the get-go.
Exactly. We're diving into a specific paper that really lays out the complexities, and they're maybe a bit surprising. It shows that designing solar cells to be high-performing and recyclable, well, it's not just about adding a recycling step at the end.
Mm-hmm.
It forces scientists to deal with these fundamental trade-offs, these conflicting demands, right from the initial design.
Okay, so our mission for you, the listener, today is to understand why making a truly recyclable solar cell is actually much harder than it might sound.
Yeah.
It's about grasping these, like, conflicting requirements scientists are up against at the deepest material level, why making something super durable for 30 years makes it incredibly tough to pull apart later.
Mm-hmm.
This deep dive is basically your shortcut to understanding this complex, emerging challenge that's really essential for solar's bright future.
And getting your head around this matters because, look, as solar becomes a cornerstone of our energy system, dealing with that mountain of old panels is crucial for genuine sustainability.
Right, it's not just waste.
No, it's about resource security. It's about minimizing environmental harm. Getting insights into these really cutting-edge design challenges. It shows you where the next wave of innovation is heading.
Okay, so let's rewind a bit. What were the main goals when engineers first started designing these things?
Well, initially, and for, many years, the focus was pretty squarely on two main things: pumping up the performance and slashing the cost.
Performance and cost. Got it.
Performance is usually measured by how much sunlight a panel turns into electricity. That's its power conversion efficiency, often called eta, the Greek letter,
Right.
AKT. And this efficiency, it depends on some pretty basic stuff about the material itself. How well it grabs sunlight, that's its absorption coefficient, alpha.
Mm-hmm.
How easily the electrical charges it creates can move through it, that's carrier mobility, mobile.
Okay.
And how long those charges actually stick around before they just, poof, disappear. Carrier lifetime, tout.
And the classic example everyone knows is silicon, right? That's been the workhorse.
Absolutely. Silicon, yeah, it dominates, and it's a great way to illustrate this. It's fantastic at letting charges move easily, that's high mobility, and letting them last a long time, so long lifetime.
Mm-hmm.
But a sort of quirk of silicon is that it doesn't absorb light super strongly. It has a lower absorption coefficient.
Ah.
So to actually catch enough light, you need thicker layers of silicon. And engineers develop these clever tricks like texturing the surface to sort of trap more light inside the cell.
And what about the cost side? Because we've all seen panel prices just plummet.
Oh, phenomenal cost reductions. It's been incredible over the decades. The overall economic picture, we capture that with something called the levelized cost of electricity, or LCOE.
LCOE.
Yeah. This includes the efficiency, but also, how much it costs to make the panel, how fast it degrades over time, the degradation rate, D, and crucially, how long it actually works out in the field, its operational lifetime, T-life.
Right, that 30-year lifespan people talk about.
Exactly. And because silicon panels got incredibly efficient, really cheap to manufacture, and they can last 30 years or even more, the cost of solar electricity just dropped dramatically.
Yep.
It's competitive with, or often cheaper than, fossil fuels now. In lots of places sometimes. Yeah, down around a cent per kilowatt hour. Crazy low.
So for the first few decades, it was just make them work great, make them last long, make them cheap, simple enough.
Pretty much.
But now, with so many panels out there, these other factors like recyclability, material supply chains, they're becoming really urgent.
Precisely. When you're deploying solar on a terawatt scale,
Yeah.
you have to think about the end of life, not just for a few panels, but for billions.
Yeah.
And we also have to consider where the materials actually come from. Are they sustainable? Are they environmentally okay throughout their whole life cycle?
Right.
And the challenge is that those early panels, the ones optimized only for performance and cost, well, they just weren't designed with easy disassembly in mind. Plus, some use materials that are, a bit scarce or concentrated in just a few places globally, like tellurium in CDT cells,
Okay.
or gallium in gallium arsenide cells, or even elements like cadmium and arsenic, which, okay, they're safely contained during the panel's life, but they definitely raise questions when it comes to recycling.
Okay, so the goal now shifts to designing for recycling. But what does recyclable actually mean for something as complex as a solar cell? It's got all these different layers. How do scientists even approach that?
Yeah, it's not simple. The research we're looking at breaks it down into several key factors, almost like a checklist for the materials and the structure. The focus is really on how easily you can separate and recover the different bits cleanly.
Got it. So what's the first thing on the checklist?
The first is intralayer bonding strength. Think of this like how strong the glue is within a single layer.
Okay, inside one layer.
Yeah, the internal bonds holding the atoms or molecules together inside one specific film. If these bonds are super strong, like the covalent bonds in silicon where atoms share electrons really tightly, you need pretty extreme conditions, like intense heat or really harsh acids, to break that layer down.
Right.
On the flip side, some newer materials like perovskites, they have weaker bonds, ionic or van der Waals forces. Maybe think more like magnets than superglue. These layers might just dissolve more easily in milder solvents. Cadmium telluride, CDT, that falls somewhere in the middle.
Okay, so how tough is each individual layer to break apart? What about how the layers stick to each other? That seems super important for taking it apart layer by layer.
Exactly. That's the second factor. Interlayer bonding. This is all about how well adjacent layers stick together. If the bond between layers is really strong and stable, like the incredibly robust connection between silicon and its natural oxide layer, CCO2, in traditional cells, then separating them cleanly is, well, really hard. You might need aggressive chemicals, maybe hydrofluoric acid, which is nasty stuff and creates its own waste problems. But if the bond between layers is weaker, maybe just relying on these non-covalent forces, it opens up possibilities for gentler separation.
Oh.
Maybe using specific solvents that just kind of loosen the grip between those layers. Some of the newer cell designs, like certain types of perovskites, they have interfaces like this, which makes, gradually peeling away layers, at least theoretically, possible.
So interlayer is the strength within a layer. Interlayer is the glue between layers. Makes sense. You mentioned there were a few key factors. What's next?
Yes, the third one is closely linked. Bonding contrast. This is about the difference in bonding strength or the type of bonding or maybe the solubility between layers that are right next to each other.
Okay, the difference between neighbors.
Yeah, and high contrast is actually a good thing for recycling. It means you could potentially use a specific chemical or process that attacks or dissolves one layer without messing up the layer right next to it. The paper gives an example. Perovskite absorber layers, they often dissolve pretty easily in certain polar solvents, right? But the metal oxide layers often used next to them, like titanium dioxide, TiO2, or tin oxide, SnO2, they don't dissolve in those same solvents. That difference, that contrast in solubility, allows you to potentially wash away and recover the perovskite material cleanly.
Okay, that's clever. Like having two things stuck together where one dissolves in water and the other doesn't. You just rinse one away. That's a clear contrast. What was the fourth concept? It sounded a bit different.
Yeah, the fourth one the source mentions is locked-in entropy. Now, okay, this isn't maybe a strict physics term here, but think of it practically. It's the degree of irreversible mixing or like entanglement that happens during the manufacturing process itself.
Okay.
It's basically what makes it really hard to get materials back into their original pure state at the end. Imagine baking a marble cake, trying to separate the chocolate batter from the vanilla once it's baked.
Impossible, right?
Right, totally mixed. That's high locked-in entropy. If you just had separate layers of chocolate and vanilla frosting, maybe you could scrape them apart. Lower entropy.
So it's processes during manufacturing that mix things up permanently.
Exactly. In traditional silicon cells, making that essential electrical junction involves diffusing tiny amounts of other elements, dopants, like phosphorus or boron, into the silicon. This happens at really high temperatures. Those atoms spread into the silicon structure permanently, or when they fire on the metal contacts, like the silver lines you see, onto the silicon, they can form these irreversible alloys. the metals literally mix and bond chemically with the silicon.
Okay.
These steps are absolutely vital for the panel's performance and stability, but they create these zones or interfaces where materials are permanently mixed up at the atomic level. And that makes clean separation and recovery super difficult. In other techs, like CDT cells, sometimes heat treatments cause the main CDT layer to actually alloy a bit with the layer next to it, CDS. That helps performance, but it wipes out that clean boundary you'd ideally want for separation.
Okay, so let me recap. We've got these 4 key things that basically decide if a cell can be recycled cleanly. How strong the materials are inside themselves, intralayer bonding,
Yep.
how strongly the different layers stick together, interlayer bonding,
Right.
whether adjacent layers react differently to separation methods, giving you that contrast, bonding contrast, and how much irreversible mixing happened when it was made, locked in entropy.
You got it. Those are kind of the material level knobs scientists can try to turn.
And this is where it gets really interesting and honestly probably a bit frustrating if you're an engineer. The paper calls this the art of designing for trade-offs.
This is absolutely the crux of the issue. The parameters you need for high performance, low cost, and recyclability. They are not independent things you can just optimize one by one. They are deeply, often maddeningly intertwined. Designing the next generation of solar cells is an art, because you can't just max everything out. If you tweak one thing, say make bonds weaker so it's easier to separate that might totally mess up something else, like making the cell less durable or less efficient.
Right.
You have to skillfully balance these goals that are often pulling in opposite directions. It's like a puzzle where solving one piece creates problems somewhere else.
Okay, let's dig into some of those specific conflicts their research points out. What about the tension between just using materials that are, common and abundant versus materials that are really good at moving electricity?
Yeah, a classic trade-off. Some materials are just brilliant at letting charge carriers zip through them. They have high mobility, which is fantastic for performance.
Yeah.
Think of things like indium tin oxide, ITO, or gallium arsenide GAs, indium phosphide, NNP.
Okay.
Problem is, these materials often rely on elements that are scarce or expensive or maybe only found in a few parts of the world. That's a major headache if you want to build things at the massive scale solar needs. It's a bottleneck.
Exactly. The more abundant and cheaper options like tin oxide, SNO2, or zinc oxide, ZNO, they're much better for huge scale deployment, but often they just don't have that same super high mobility. So that might limit the absolute peak efficiency you can achieve with them.
So you might need to accept slightly lower top performance to get something you can actually make billions of. Okay, what about the conflict between making layers easy to separate using that bonding contrast idea and how well the electricity actually flows across that boundary?
Oh, this is a really critical one that designing for recyclability brings right to the forefront. Remember how high bonding contrast is good for separation?
Yeah.
Well, sometimes having very different types of materials right next to each other, maybe a soft, flexible organic layer next to a hard, crystalline one, creates a really stark difference, physically or electronically, right at that interface. And these big differences can create imperfections, like little electronic potholes or traps where the charge carriers get stuck and just recombine instead of flowing through to generate power. Bad for efficiency.
Exactly. It reduces their lifetime, which directly hurts the cell's efficiency. So, paradoxically, making the interface easy to break apart for recycling can actually make it electronically messy, harming performance. This is something they wrestle with a lot in perovskite cells. Those interfaces need incredibly careful engineering to work well electronically and hopefully be easy to disassemble later.
Fascinating. So making it easy to pull apart might make it harder for the electricity to get across smoothly.
Okay, and what about that locked-in entropy, all that permanent mixing during manufacturing? How does that clash with making the panel perform really well?
This might be the most direct conflict with how solar cells have been designed historically. Almost every trick in the book used to boost performance, adding those dopants, creating alloys, engineering complex stacks of multiple layers with carefully tailored interfaces. Using high-temperature processing, these things often increase that locked-in entropy.
Doping silicon and firing on those metal contacts are perfect examples. These steps are absolutely essential for creating the buried electrical junctions and the low-resistance connections you need for high efficiency and long-term stability. They boost how well carriers move and reduce losses.
Right. Crucial steps.
But the result is permanent, irreversible chemical mixing at those interfaces. And that makes it much harder and more energy intensive to get pure, reusable materials back out at the end of life. It's basically a performance win now, but it comes at the cost of clean separability later.
So the more complex and tightly integrated you make the structure to squeeze out every last bit of efficiency, the harder it becomes to dismantle. Is that true structurally too, not just chemically?
Oh, absolutely. High-efficiency solar cells often have incredibly intricate physical structures. We're talking about, textured surfaces to capture more light, stacks of super-thin layers to passivate the silicon surface and improve the electrical contacts, buried junctions created by diffusion, complex multi-layer anti-reflection coatings.
No.
These features are brilliant engineering for minimizing energy losses and hitting record efficiencies, but they create these densely integrated structures. Even if you could somehow magically reverse the chemical mixing, the sheer physical complexity and the strong bonding needed between all these layers make just mechanically or chemically separating them incredibly difficult. The very structure optimized for performance actively resists being taken apart.
And then there's maybe the most obvious one. When you just look at a finished panel, it has to survive outside in all sorts of weather for decades. How does that fundamental need conflict with making it recyclable?
Yeah, this is a huge one, a massive hurdle. To protect those delicate active layers of the solar cell from moisture, heat cycles, cold, impacts, hail, you name it, for potentially 30 years or more.
Right.
Panels are encapsulated. They use these incredibly durable materials, most commonly a polymer called EVA, ethylene vinyl acetate. It's usually laminated under high heat and pressure. This process creates extremely strong, stable, and often pretty much irreversible bonds between the front glass, the solar cell sandwiched inside, and the protective back layer, the back sheet.
Built like a tank, basically.
Exactly. And that permanence is fantastic for keeping the panel working reliably for decades out in the field. But it makes taking that sandwich apart at the end of its life incredibly difficult.
I bet.
It often requires pretty harsh methods, like burning off the polymer in a furnace that's pyrolysis or using really aggressive chemicals to try and dissolve things. Neither of those is ideal if your goal is to recover pure, high-value materials that you can reuse. The very thing that guarantees its long life actively resists its return to the material cycle.
So it's not just about being able to break it apart somehow, but breaking it apart cleanly enough that the materials can actually be reused effectively, right? To make new panels or other high-value things.
Exactly. That's the key. The goal isn't just diverting waste from landfill. It's about establishing a true circular economy for solar, where these valuable, sometimes critical materials are recovered efficiently and can re-enter the supply chain.
And that brings us right back to the core paradox this paper really drives home.
It really does. It's this fundamental tension that's kind of built into the materials and the design choices. The very features that make solar cells incredibly robust, stable, and high-performing out in the harsh real world. The strong internal bonds within layers, the robust interfaces between layers, the tight structural integration.
Yeah.
Those are precisely the features that make them inherently resistant to separation and clean material recovery when they finally wear out. It's a direct, almost unavoidable conflict between optimizing for permanence and durability versus optimizing for circularity and reversibility.
Wow. So what does all this mean for the future then? Does it mean we just can't have solar panels that are highly efficient, durable, and recyclable? Is it an impossible combination?
No, not at all. It doesn't mean it's impossible. It just means the challenge is much more complex than maybe people first thought, or than just, building a recycling plant at the end.
Yeah.
It means the next big phase of solar innovation isn't only about pushing efficiency numbers even higher, it's fundamentally about cleverly navigating these really complex, multi-objective design trade-offs.
Right.
It's about finding new materials, maybe new cell structures, new manufacturing processes that somehow manage to strike a better balance, balancing performance, cost, durability, and embedding that end-of-life recyclability right from the beginning.
And there is real opportunity here, isn't there? Especially perhaps with some of the newer solar technologies that are coming up.
Definitely. Technologies like perovskites, which we mentioned, other types of thin films, and maybe tandem solar cells, those are the ones that stack different materials to grab more of the solar spectrum. They kind of offer a fresh start.
A clean slate.
In a way, yeah. Many of these use different materials and different manufacturing processes that might just be inherently more amenable to disassembly and material recovery compared to traditional, heavily processed silicon. They give scientists and engineers a chance to actually design circularity from day one, rather than trying to figure out how to recycle structures that, frankly, were never designed with that in mind.
That feels like a genuinely exciting direction for solar's, bright future. Can we really design materials and interfaces that are both incredibly durable, surviving decades of sun, rain, heat, cold out in the field, and somehow easily reversible when their job is done, allowing those valuable materials to just flow cleanly back into the manufacturing cycle. It's a massive engineering puzzle.
It absolutely is.
Yeah.
And, this isn't a challenge that's unique just to solar. When you stop and think about it, where else in technology? I mean, think about electronics, batteries, even construction materials. Where else do we see this fundamental tension between creating something that's built to last maybe for decades and needing to design it with its eventual end of life actually factored in, aiming for true circularity? It's a design principle or maybe a design challenge that's going to shape so many industries as we move forward towards a more sustainable economy.
Definitely a lot to think about there, about how we build pretty much everything around us for a more sustainable future.